have the data for your brine shrimp experiment?
Yeah, I wrote it all down in my journal.
Great. Let's use the data from beaker A to plot a graph.
For the first few days, there was not much growth in population size, since the eggs were just hatching and the shrimp were maturing. This is called the lag phase, a period of very little growth. But in the following days, the number of births was high. This is called the growth phase, a period of very fast growth. Then there was a period of no growth. At this point, we figured that the number of shrimp being born was equal to the number dying. This is what is known as the stationary phase. On the following days, the food supply was probably close to being depleted, since there was a sharp decline in the population. Plus, there was a buildup of waste and a lack of oxygen. Soon after that, all the shrimp died. This is the death phase, where deaths exceed births.
Good job, Cam. Now, how about the growth curve for an open population? Does it show the same phases as the one for a closed population?
No, it doesn't show the death phase.
Could you explain the growth curve for an open population?
Some open populations tend to exhibit what is called a sigmoidal growth curve. They show a lag phase and a growth phase, and then the numbers tend to stabilize. This results in an S-shaped curve. Other open populations tend to show cyclical patterns of growth. Population increase is followed by a sharp decrease and then increase again. This pattern repeats. Still, other open populations increase and decrease, but don't have a regular pattern of growth or decline.
Okay, we're getting closer to being able to do some population prediction. What we need to do now is figure out a way to calculate population growth rate.
You mean how quickly or slowly a population is growing over time?
Exactly, and that is expressed as a percentage. The shorthand for it is PG %. Does anyone know the formula?
Population growth rate is the change in population size, or delta N, divided by the total number in the population.
Joelle, I think you are missing one piece of information in there.
Oh yeah, times 100.
Exactly. So now, using this formula, we can calculate the daily growth rate of the shrimp population. Let's calculate the daily growth rate for population A.
Okay, well, between yesterday and today, delta N was negative 2.9, and N was 35.9. So the growth rate would be negative 2.9 divided by 35.9 times 100. Hey, that's negative 8%. Is that right? Can a growth rate really be a negative?
Yes, it can. Now, the question I have for you is, at what phase of the growth curve would you expect this type of result?
Probably the death phase.
Right.
So you mean if I would have used results from the growth phase period of time, my results would have been positive?
Exactly.
If we know the rate of growth, does that mean we can figure out how big the population will get in the future?
Well, yes and no.
What do you mean by that?
Well, let's look at the yes part first. In theory, if none of the factors that affect that population change over the period of time that you're calculating the growth, then yes, you can calculate population growth. We need to use this formula. I is equal to R times N. This is the formula for population increase. R represents the growth rate and N represents the population size. So this formula then we can use for calculating the increase of a population for one generation after the next.
So we could calculate what a population would be in, let's say, 10 years?
Well, in theory, yes. But remember what I said before. None of the factors affecting that population for those 10 years can change. Now, let's calculate the growth of the shrimp population for 5 days. Let's start from day 5 and go up to day 10. That way we can compare the calculated numbers with the ones that you're going to be predicting. Okay, let's start calculating. are you finished your calculations?
Yep. The predicted populations for beakers A and B is 78.
And the actual for A is 45.
And the actual number for B is 76. And that's closer to the predicted number for B.
One reason the brine shrimp population in beaker B was closer to the predicted number might have had to do with food. We fed them every 2 days during the entire test period, but the shrimp in A were only fed that once, day 1.
Good analysis. Now, the formula and example we use is very simplistic. Ecologists actually use a more complex formula to do population analysis. They use I equals to R times N times K minus N in brackets divided by K. Let's analyze this formula.
So I is population increase. What's the R?
Well, the R stands for intrinsic rate of natural increase. It represents the difference between birth rates and death rates. And you know what the N stands for, right?
N is population size.
And I remember that K stands for carrying capacity of the environment.
That's right. Do you remember the definition for carrying capacity?
I think carrying capacity is the number of individuals that an environment can support.
That's right. Do you remember the factors that affect the carrying capacity?
Well, predation and competition would be 2 of them.
Food supply and temperature changes would also affect the carrying capacity.
Yes, you're both right. Now, by including K in the formula, we are taking into account those factors.
So, ecologists use this formula to make their population predictions more reliable.
That's right. But now let's move a little bit closer to home. Let's talk about human populations. How many of us are there?
3.
In the world?
It's closer to 6 billion, and it's getting pretty crowded.
It wasn't always so crowded. I've been doing some reading on human population growth, and I found some interesting stuff.
Well, let's see.
For 10,000 years, the human population on Earth was relatively small. But in the last century, there's been a huge increase in the number of people on the planet. This is called exponential growth. The rate of growth is due to a variety of factors, such as improved living conditions, better nutrients, and medical services. Some demographers predict that the human population will continue to increase, reaching approximately 12 billion by the year 2042. 12 billion people. That seems really crowded.
Sooner or later, we're going to hit a limit.
You know, we're probably going to end up running out of food or energy.
Or space.
What about disease? Won't infections spread quicker? Remember the plague? Wasn't one of the main reasons it spread so quick because of overcrowding?
Does that happen again?
Well, first of all, we can't predict population. All we can do is, in a sense, give an estimate or get projected figures of what the population will be in the world or in various countries, given that the existing conditions continue. Population growth in the world is becoming a problem. Some areas it's more acute than in others. For example, everyone is familiar with the fact that China has the largest population. And but in a sense, their rate of growth has been declining because of their effective program in reducing population growth, reducing fertility.
So what are the environmental impacts on these countries that have large number of people?
The problems of this disposal of waste, the problems of food supply and preservation and so on, periodically create epidemics and break down so that they have extremely high mortality rates, yes, particularly infant mortality rates. In Canada, for example, the population growth rate is declined to the point where we're concerned about the aging population, so we have quite a different problem.
What are some of the factors that have led to such high numbers in populations?
The population explosion actually began with the European countries in a time of industrialization and development.
There are almost 6 billion people on Earth. By the year 2042, there could be 12 billion.